7.3 logarithm functions. So you're going to need to write each exponential equation in logarithm form and each logarithm equation in exponential form. So for second period in red, write 9 squared equals 81 in logarithm form and log of 10 equals 1 in exponential form. For third period in green, 3 cubed equals 24 in logarithm form and log base 12 of 144 equals 2 in exponential form. For fifth period, in pink, 3 to the negative 4 equals 1 over 81 in logarithm form, and log base 1/2 of 8 equals negative 3 in exponential form. For sixth period, in orange, 4 to the 1/2 equals 2 in logarithm form, and log base 3 of 1 over 81 equals negative 4 in exponential form. And this is due on Wednesday as soon as you come into class. So a logarithm is the exponent to which a specified base is raised to obtain a given value. So you can write an exponential equation as a logarithm equation and vice versa. So for exponential equations, we write it in the form of b to the x equals 8. And for logarithm, we write it as log base b of 8 equals x. So your b goes here, your a goes here, and your x goes here. So let's do an example. What if I have an exponential equation, 2 to the 6 equals 64, and I want to write it in logarithmic form? Well, I'm going to start with log of base 2 of 64 equals 6. Let's do another example. What if we have 5 to the 0 equals 1? And I want to write it in logarithm form. What's going to be log base 5 of 1 equals 0. What if we have 3 to the x equals 81? And it's going to be log base 3 of 81 equals x. Now what if we're turning a logarithm equation into exponential form? Well, we have log base 7 of 49 equals 2, then it's going to be 7 squared equals 49. If we have log base 5 of 5 equals 1, then we're going to write it as 5 raised to the 1 power equals 5. One more. If we have log base 12 of 1 equals 0, then it's going to be 12 to the 0 equals 1. So as you can see, a logarithm is an exponential. So the rule for exponentials also applies for logarithms. Some special properties to remember is that if you have log base b of b, it's going to equal to 1. For exponential, we know that b raised to the 1 power is just b. An example would be if we have log base 10 of 10, that's going to equal to 1. For the exponential, if you have 10 to the 1 power, that's just 10. Another one is log of base b to the 1 equals 0. What does that mean? Well, that b to the 0 is going to equal to 1. So an example would be log of 10 to the 1 equals 0. And for the exponential, well, 10 to the 0 is 1. Any number to the 0 power is always going to give you 1. We also have what it's called a common logarithm. A common logarithm is a logarithm with base 10. So if you have log of 5, this is the same thing as having log base 10 of 5. So you're not going to see it, but it is actually there. It's a base 10. So now let's evaluate logarithms. So if I have log of 100, like I said before, there's a base of 10. So this is the same thing as saying log base 10 of 100 equals a number. So to solve this, we can write it in exponential form as 10 to the x equals 100. Well, 10 to what power gives us 100? Well, 10 squared gives us 100. Then we can say that x equals 2. So then our solution would be log of 100 equals 2. Let's do one more. What if we have log base 2 of x equals 3? Well, I can write it in exponential form as 2 cubed equals x. Well, 2 cubed is just 8, so 8 equals x. So then our answer would be log base 2 of 8 equals 3. So what if we have log base 7 of 1 over 49 equals x? If we write it as an exponential form, then we can write it as 7 to the x equals 1 over 49. Well, 1 over 49 is the same thing as 1 over 7 squared. And 1 over 7 squared can be written as 7 to the negative 2. Then x is equal to negative 2. So then we can write it as log base 7 of 1 over 49 equals negative 2. Now for graphing, logarithm functions are the inverse of exponential functions. So we have f of x equals 2 to the x. And we want to find the inverse. Well, we start by rewriting this function as an equation. So y equals 2 to the x. Then we switch the x and the y. So then x equals 2 to the y. Now if we turn this exponential equation into a logarithm form, we can write it as log of base 2 of x equals y. And if we're graphing, we have f of x equals 2 to the x. Since b is greater than 1, then it's going to be an exponential growth. That's going to look something like this. The domain is going to be all real numbers, and the range is going to be all y's such that y is greater than 0. Now if we're graphing the inverse, f inverse of x, which equals log base 2 of x, it's going to be reflected on the line, reflected across the line y equals x. So it's going to look something like this. So the domain and the range for the inverse function is going to be the range of f of x. So then x such that x is greater than 0. And for the range, it's going to be the domain of f of x, which is all real numbers. Let's do one more. What if we have g of x equals 1 over 2 to the x? Once again, to find the inverse, we're going to rewrite it as an equation. So y equals 1/2 to the x. Then we're going to switch our x and y. So x equals 1 over 2 to the y. Now we want to write this exponential equation into logarithm form. So it's going to be log base 1/2 of x equals y. So then G inverse equals to log base 1/2 of x. If we're graphing, G of x equals 1/2 to the x, b is less than 1, so it's going to be an exponential decay. So it's going to look something like this. And the domain, it's going to be all real numbers, and the range is going to be all y such that y is greater than 0. Now if we're going to graph G inverse of x, which is log base 1/2 of x, it's going to be reflected on the line y equals x. So it's going to look something like this. This is G of x, and this is G inverse of x. So then the domain, it's going to be the range of G of x, which is going to be for all x's such that x is greater than 0. And for the range, it's going to be the domain of G of x, which is all real numbers.
Is that it?